but I am a chemist, so it is something.
Okay.
So,
That's good.
yeah, is it really? So this paper is great if you want something short and sweet.
Yeah.
It's all thermodynamics based. The whole point of this paper is silver is a catalyst. What is the most stable oxygen species in silver when it is a catalyst? That is the whole goal of the paper. Very simple. So I just wanted to throw this up. One of the most prominent reactions it's talking about in this is an oxidation. So you have an alkene on the left, and you have some kind of agent that oxidizes. So that could be air, that could be a catalyst, like silver. And then you make an epoxide. So it's like a little triangle, and you have an oxygen right there. And this is used for everything. Think like epoxies, glues, plastic, a bunch of stuff. So sticky stuff. Well, also just regular stuff. Everything. Drugs. Whatever. So it's really important to have a good catalyst. So what makes a good catalyst in general? You need the species, the beginning species, so let's say that alkene. You want it to readily bond to your catalyst. You want it to come on, but you also want it to dissociate really fast. So readily dissociate, add particles, so finished product, but you also want it to bind strongly the starting reactants. So silver binds really weakly in general, so you'd think, oh, it'd be a shitty catalyst, but it's a really good catalyst, so that's why everyone's confused. It's commonly used for those two reactions. The paper talks mostly about the epoxide reaction, so everyone's like, how is this possible? So no one knows what the active oxygen species is for this reaction. These are the options. So we can have bulk dissolved oxygen, which is where the oxygen goes from the environment into the bulk metal. We can have on-surface sites, so we have surface available oxygen terminated sites. We have surface and bulk substitutional sites, so you have the oxygen replacing some of the silver in the actual lattice structure, and that can be on the surface or in the bulk. Whereas bulk dissolved is the oxygen's just kind of moving around. Think interstitial versus vacancy kind of situation. And then we have interstitial sites under the gold surface. I think that's self-explanatory. Oxide-like structures. So think when you have metal and then you have rust. So you have rust on the surface. So if you think about a silver particle, you're going to have an oxide layer on the surface. That's in the oxide-like structure. Ozone-like structure. Ozone is O3. So you just have an inserted ozone structure instead of an oxide-like structure. But that's not very likely, so we don't have to deal with that much. So the goals of this paper, we want to quantifiably look at active oxygen species in the silver catalyst in a high vacuum environment. Ultra high vacuum. Again, think the MBE environment. Super clean. The reason we're going to use a high vacuum environment is because we need to look at this at high pressures and temperatures in which these catalytic reactions happen. And if we do it in a normal environment, we're going to have a bunch of other crap going on, and it's going to be really hard to tell what actually is going on with the active oxygen species. So when we're doing the DFT simulations, we want to make sure we're already assuming, I think it's like 10 to the minus 12 torr or something, which is kind of crazy. Yeah, right?
Pretty
well,
impossible.
It's DFT, so because it's trying to make a theory, right? It's trying to use this as the base for pretty much any metal oxide catalyst. Talks about ruthenium a lot and gold catalysts, and use this as a model system. So it used a density functional theory to make, or at least figure out, the thermodynamic energy levels for all of these different relevant species, even the ones that aren't super relevant, and then find out which ones are most likely to exist in the system at a certain pressure and temperature and also crystal orientation. So it looks at those different things. And again, stop me if you have any questions. So I also wanted to throw in key terms. So this is the scary density function theory, section. So there's the pseudo plane wave theory method. So it's an approximation for the wave function of atoms. So I threw in this picture. And so you have your true wave function for an electron or an atom or a species, and the pseudo wave function is making a basic approximation to simplify the calculations so they can be done in real time.
So a nicer sine wave, basically.
Exactly, and you use this for periodic systems, so think lattice structures, but you don't want to use this for systems that are not periodic, or else it's going to just repeat the same things over and over again.
So density functional theory is a lot of just modeling solids.
Yes.
You can do that.
Yes. So it's just this is just the method it uses to model the crystal structure. And then I included this link. It's like 40 slides of someone who just explains densital functional theory in like the basics, absolute basics. It's super great. And even like includes the basic equations that they use and eigenfunctions and eigenvalues, whatever.
Yeah.
So it's great. I would highly recommend looking at those slides. And then here's some other terms. So the generalized gradient approximation. So when you use the plane wave approximation, it overestimates the binding energy. There are different types of bonds. There's the GGA, which are bendy bonds, and the LDA, which are stiffer bonds. So you use the GGA when you have systems that are a little more in flux, apparently. But basically, it's an approximation of the binding energy. Anything more specific than that, I would talk to someone else. There's the exchange correlation function. So this allows you to approximate the uncertainty with the actual calculations itself. And then there's the K point, and this is, I think, the most important thing to know. It's points within the, I should have put the other zone first. The Brillouin? Is that how you say it?
Brilliant zone, yeah.
No, the
Okay.
brilliant zone.
Oh, and the brilliant. Oh, I like that
Something
better.
that's
Is that the French, British, something?
Yeah, I had it somewhere. I don't remember.
So
But this
in
is
the
better for
brilliant-
materials, right?
In materials?
Yeah, in
It's
crystals.
space.
Yeah, it's
Yeah.
the reciprocal space. So
Yeah.
the Brillouin zone is, I have two different definitions, so both are helpful. So like a set of points where you don't interact with another Bragg plane, or a Bragg plane which doesn't have the particular wave function have constructive interference, not deconstructive interference. So
K space, yeah.
and then the K points are spaces within the Bernoulli zone that is reciprocal space, basically. And you pick specific spots. And the more spots you have, the more K points, the better your approximations are going to be. Excuse me.
You
And
just
then-
know more of the lattice, basically.
Yeah, or you have more more chances. Yes, you have more areas within a lattice.
Yeah.
It's like having a simulation that's 3x3 versus 10x10.
Okay.
Mm-hmm.
Because
And
there's
then-
still the brilliant zone, whatever, inverse space is still the lattice.
Yes.
So, yeah.
Yeah, it's definitely still lattice. You can have all those things and not talk
And when we
about.
talk K spaces, is the same thing, right? K
Yeah.
points in reciprocal
Are in the
space,
brilliant zone is in reciprocal space.
Yeah,
which are K.
which is K
points.
space, but
Yeah.
K
Momentum
points
space, whatever you
are
call it,
specific points within that
K,
space.
yeah,
That-
exactly, yeah.
Are with the lattice.
Yes.
Okay.
Yeah.
Mm.
I
Wow.
guess if you
Point that
Google K point, it'll give you two different. It'll give you the lattice structure definition and the computer science definition.
The symmetry thing,
Mhm.
it's more so, yeah.
So it's kind of.
It's the symmetry thing is what they're referring to.
Yeah.
These, yeah.
And then ML, I just also threw that in. Number of adsorbates per number of surface metal atoms. It's a term that they use for a few different papers, like coverage value. So think of it just as a unit. So the higher that number is, the more things absorbed on a surface. Okay. Cool. I don't think they'd ask anything more in depth than
Yeah.
that
No.
for
I don't think so.
the computational stuff.
Great.
So, and then just go over what they actually figured out. On the right is a graph. It's a little confusing. The bottom is coverage in ml. So as you increase to the right, you have more oxygen. And then on the left, the y-axis, you have adsorption energy. So as you increase, things are getting less favorable. So you want to be down, and the oxygen coverage, that just depends on the amount of oxygen in the environment. So I tried to highlight green, the section that we like the best. So that's that red line with the boxes. That's the most favorable one. Everything else, they have on-surface absorption. That's the red diamond, the one that's really long. That's FCC hollow. So another thing I could also see them asking is like, what's an FCC hollow? Draw that. You know, really simple. Just make sure you know what your shapes are. And then bye. Good luck.
Bye.
And then there's subsurface absorption and bulk dissolved. So those are on the top. So you can see those are the blue ones, I think. There's bulk substitution, surface substitution, bulk octahedral. So all of those are in an octahedral geometry. So you can see they have a little picture of it. Subsurface octahedral for the black line. It's a little, I really don't like this graph. It's really confusing.
It was so confusing. I was like, I'll learn this eventually.
Yeah.
But I didn't like it.
So the only thing you really need to care about is the green section that I highlighted that has the 4x4 and the oxide-like structures. So what they refer to as 4x4 is also known as a thin oxide layer. So they say 4x4, I'm not really sure why they call it that. They use the two terms interchangeably. It's just like a super thin oxide layer that doesn't have a ton of oxygen. Whereas when you go to the right of the graph to coverage ML, like 1.2, you have oxide-like structure, and that has way more oxygen. So you take the 4x4 and then you add more oxygen, and it basically puffs up. And that's still favorable to exist, but that isn't necessarily as reactive as we'll see later on.
Is there a threshold by which you would say above this stuff will not exist?
Not necessarily in this graph, but I would say like where that green like is, everything above the ozone, I would say don't worry about that.
Okay.
And that's basically the point that they made. They said that the energies are too high for bulk and all the surface stuff. They're like, it's just unfavorable.
Okay.
And that's all they say.
So the 4x4s aren't necessarily surface structures? Or are surface structures different than oxides?
That's a great point. So imagine an oxide, but it's like the very first layer of an oxide that's super, super thin.
That's a 4x4?
Yeah.
Oh, all right.
So it just doesn't, hold on, let me go back to this image. So you can see here, it has bulk oxide, surface oxide, and then it has clean surface. So the 4x4 is what they refer to as the surface oxide. So it's the oxide in between the bulk oxide and the clean surface.
Yeah.
And that was what they say is the most reactive.
And then is this like 1/16, 1/9, whatever? Is that them adding more oxygen to create the oxide-like structure?
Yes.
Okay.
So as you decrease the ml, you get closer to the clean surface. And and there's some more graphs on that. But over here, all subsurface sites, they're going to be, some of them are more favorable than others, but if you think about the layers, the first layer is always going to be more favorable than the second layer. So if you think about the picture we just saw, the bulk oxide, let's say that's layer 1, surface oxide is going to be more favorable than the next layer, than the next layer, than the next layer.
Okay.
So oxides are the most favorable. That's what you need to know.
And that's just because if you're in an environment with like oxygen, it's just easier to form the oxide it's just like diffusion kind of thing?
Yes.
Okay.
Yeah, exactly. And then as you get closer to the inside, you are less likely to diffuse more oxygen in.
Okay.
So, but then they also mentioned this like 0.5, 0.75, 1, and 1.25, 2x2.
Yeah.
That's different than the 4x4.
The 2x2, where's the 2x2? What page?
I saw it, I'm reading this like it's just above that chart, that weird, horrible chart.
They say 0.5, 0.75, 1. Oh, using 2x2 cells. That's like the area in which they investigated for the DFT calculations, I'm pretty sure.
Oh, okay.
I think they were just looking at 2x2 cells.
Yeah, because this is like to investigate the formation of oxide-like structures. They did this, whatever, using 2x2 cells. And then in addition to that, they also did 4x4
Mhm.
thin surface oxide structures.
Yes.
Okay.
Do they specify which one is which on the graph?
No, that's
No.
why I was confused.
They don't.
Because then they do like 0.5, 0.75, but then when they talk about the 4x4, they're using like 1/16, 1/9, 1/4, and
Right.
I got confused. I think that's where my confusion was like the difference
is
between the
super fair.
2x2 and the 4x4. But I knew that the 4x4 clearly was like favorable, but I was like, what's up with the 1/16 and 1/4 situation going on?
Yeah, they don't really specify the difference between the 2x2 and the 4x4. I think they, for some reason, it was just like they did calculations for a 4x4 and found that thin oxide structure.
Yeah.
And they just didn't do that for the 2x2.
Okay.
Or that the thin oxide structure, it needs to have 4x4 cells in order to exist.
That's what I was thinking too. Yeah.
Yeah, so that could be it.
Okay.
Wait, there's a 2x2?
So then this 1/16, 1/9, 1/4.
Yeah.
I'm assuming that's like thickness
That's the
after the 4x4 surface layer.
That's just
No?
the amount of oxygen that's in the species. So it's not
Oh.
necessarily the 4x4 layer.
And the
Okay.
more that coefficient next to it is, like the more reactive it would be because it has more oxygen in it or something?
Not necessarily. So it depends on the crystal structure, which is what this plot was saying. Well, no, this was
Oh,
giving you
okay.
what crystal structures are possible.
Mhm,
Yeah.
And it's saying you could have a thin oxide or a regular oxide.
Okay.
And then the next graph, so this is about surface free energy diagram. So it says, okay, what's most favorable or what has the lowest surface energy? Which structure predominates? And that's gonna be the most likely structure to react. So, for this,
Okay.
yeah, I think this graph will help. It took me a while to understand actually what this is saying, 'cause it's very confusing. Everything, if you see the graph, everything in red, don't worry about that. Because we only care about the lowest surface energy. So if we look at, and surface energy is the y-axis. If we look at -10, and we look at the top, and each line dictates a different structure. So the gray line is clean surface, middle line is absorption, green line is surface oxide, and that's that thin oxide, 4x4, whatever. And then yellow is oxide, full oxide.
Ah, I see.
So if we look at the 1/16, 1/9, 1/4, all those lines, they're in the clean surface section when we're at low surface energies, and they're going to be predominantly in the absorption structure area. If we look at the 0 line, for example. So chemisorption is more favorable than forming an oxide. So those are not going to be prevalent when we're talking about doing the actual catalytic reactions with the amount of oxygen that's in the species. And then if we talk about the 4x4 structure, we look at 0.375, which is, can I zoom in? Oh,
Nice. Yeah, I wasn't
it's
seeing
that first one. See the 0.375?
Yeah.
So that's going to be more in that surface oxide absorption area. That's going to be more of an intermediate to the both. So think like the perfect combination of absorption and oxide. That's going to be that 4x4 structure. That's super stable at room pressure and 500 K, which it correlates the temperature based on chemical potential down here. So 500 K is going to be like, right in between there, and if we go up, it's right on that line. So, no. Okay. So if we look at where that intersects, it's like right there. So that has the sweet spot for the right kind of structure. It's the right kind of surface energy. It has the lowest surface energy in comparison to the 16, the 9, the 4, because that line is higher, right?
Okay, yeah.
So it has, if I took a line right at that 583 temperature, does everyone see that? At like -0.6 chemical potential? If I took a line, whatever the highest point is, that's gonna be my most favorable structure at the oxygen concentration, and that's gonna be that red line at 0.375.
And you're also saying that lower surface energy is like more like likelihood of absorption?
Lowest surface energy is whatever structure is gonna be prominent at that specific
I
chemical
see.
potential,
So
also temperature.
I see, okay.
So at, let's say, 750 Kelvin,
Mhm.
we're gonna still have that 0.375 amount of oxygen prevalent, which is, or also happens to be, the 4x4 thin oxide, surface oxide structure.
Okay,
Whereas if I go to 230 Kelvin, I'm gonna have more of an oxide surface that's more prevalent. So, if that makes more sense.
this makes more sense, yeah.
Okay. And then when we go to higher oxygen concentration, 0.75 and up, we have those other red lines. Those are gonna be more where thicker oxide is more stable over chemisorption. So if you're thinking about higher temperatures, so the other reaction that I was talking about, the formaldehyde reaction, you're gonna probably think that's a more stable structure.
Okay, does this graph show the temperatures?
Kind of. So it shows it kind of in relating to chemical potential, but I would look at this one, because this is the temperature and pressure phase diagram.
Yeah.
So if we think about, okay, I have a high temperature and a low pressure, then I'm gonna be more in that clean surface area. If I have a really high temperature, I'm gonna be all the way in that bulk oxide, you know? So if I'm looking at this on the exam, I would just look at this graph, number one, because it's gonna tell you everything you need to know. But if it asks you more specifics about the chemical potential, you might need to understand, okay, they got this from the surface energy. That's how they figured out what was the most favorable at X pressure and X temperature. So from this, it says that surface oxide is the most active at room pressure and the temperature 500 used for the epoxide reaction. You're going to have a different active species depending on what the pressure is and what the temperature is. So it does not mean that surface oxide is always going to be the most active species. It depends on what your environment is. And then, important to note, this does not take into account kinetics, like at all. So we don't know what diffusion's doing, we don't know anything. We just know, okay, X species is possible and more favorable.
Okay.
So, does that mean anything? I don't know. Yeah. And then if we think about what they can ask from like core class perspective, I would just brush up on your surface kinetics stuff. Kinetics, surface thermodynamics. So you have the energy of your bulk system, and then you have the energy of your surface. And if we're thinking about the basic thermodynamic equations, you have TS minus PV plus, the number times the chemical potential plus the surface energy times the area.
Yeah.
Can you do this? Did they talk about like the surface shape and stuff?
They didn't talk about shape.
The shape, yeah,
They
because
didn't
like
say shape.
in thermal.
Now, if they say
Yeah,
this is a
you think
circle,
about if there's a
Yeah.
a curved surface or like
that's
a
totally a possible question.
flat surface, yeah.
So that's why I would probably have this. They have a similar equation in the paper, but just have this generally in your brain, where it has the surface energy is equal to 1/2 the area times the Gibbs free energy of the overall surface, and then that's minus the summation of the number of species and the chemical potential of each species at a given temperature and pressure.
Okay.
So I would just make sure that's in your brain, because they could say, write a basic equation for oxygen, 100 oxygens, atoms, whatever.
Right.
And then from this paper, they calculate the surface energy, and they start over here. Just
They
went
do
over
like a
this.
derivation and stuff.
A little, not really, which is why I think they could ask this.
Yeah.
So they give an equation for surface energy. Again, we see that surface Gibbs free energy. And they explain what that G is, which is the G of the overall interface slab, the surface slab, and then also the underlying bulk substrate. So they already do the delta. And then again, they have the summation of those terms. So they have the number of silver times the chemical potential minus the number of oxygen times the chemical potential. So saying the same thing as that equation earlier. And then they say a bunch of things, and then they relate the chemical potential of oxygen to everything on the right-hand side. I think they could totally ask, how can we get from equation 1 to equation 2? I think that's totally fair to ask. And basically what they do is they substitute in the energy level they rearrange the equation so that the chemical potential of oxygen,
The subject.
yeah, so they solve it for the chemical potential of oxygen. And they rearrange it and substitute some stuff so that instead of having the chemical potential of gold or silver, you're going to have the chemical potential of the partial pressure of oxygen related to the partial pressure of the environment.
They write everything in terms of oxygen in the second equation
Yes.
instead of silver. Okay.
And then they also use, if you're wondering where that E total comes from, I'm going to throw this in too. They calculate the E total. They might ask this too, like, how do you calculate E total? So they use the resulting bulk silver oxide, and they extract it by just silver by itself.
Okay.
So they're just trying to get isolate the oxygen energy from the silver energy. So they have like silver and oxygen energy minus silver, and then minus the enthalpy of the silver and in the silver oxide in the bulk, just to get the O2 on the surface.
Right. Makes sense.
So that's kind of where that comes from. They explain it kind of okay in here, but this derivation where they go from 1 to 2, they don't explain that very well. And I haven't like sat down to try to go through it, but I definitely think that would be a worthwhile thing to do.
Yeah, I think we can try it on our own and see.
Yeah.
So we can discuss it.
Because this feels like a very good thermo paper.
Yeah.
Because other than that, I mean, that's pretty much it for the
Yeah.
thermo equation.
Unless there's already ask like a lot of DFT questions.
But like, what can they do? I mean, they can't. That's literally all the different forms. Like, that's all they have in the paper. It's just a paragraph. So, so what I think they could ask is what's the most favorable oxygen species for the two different types of reactions they talk about. So for the epoxidation and the formaldehyde, and then you just have to go through the reasoning of which is more stable at a specific temperature and pressure. And then I assume they're going to ask to derive the equation from 1 to 2, because I've seen that on some other questions, where they're like, how do you get from 1 to 2? And then maybe they'll just ask a really simple, like, draw this structure, what this would look like. What's the ozone structure? What would that look like? But
that's important to know. I remember hearing that.
yeah, but I don't feel like the questions they could ask could be super crazy. I mean, maybe some simple stuff about the DFT, but other than that,
Do you mention this last point because they mentioned that a lot in the paper? Like the methanol to formaldehyde.
they don't. They mention it once.
Oh,
Which is why I think they can
Okay.
ask it. Because they mentioned the epoxide one a ton, but they mentioned the temperature in the beginning of the other reaction. So if I was making a question about this, I would say, okay, you understand why the epoxide happens. What would you do if it was this reaction? Where they give you the temperature in the paper.
yeah.
So you could figure it out. Given everything provided, you know? I think it would be kind of a mean thing to do, which is why I put it in.
Yeah, I'm curious like how someone would go about determining the O species for
Oh, yeah.
like a new reaction, I guess.
So it says, in the beginning section, it says partial oxidation of methanol to formaldehyde carried out at atmospheric pressure and temperatures of 800 to 900 K.
Mm-hmm.
Excuse me. So atmospheric pressure, you're gonna have 0, right? Log of 1, what's the log of 1?
0, I think.
Is it? Okay, so you're gonna be in that middle line
I see.
where it says 0.
Mm-hmm.
And then if you go down here, so let's go to 500. 500 and 0, you're gonna be right where that X is.
Yeah.
So that's where the epoxide would be.
Okay.
Now if we go
so
to
for now,
800
Oh.
and 0, you're gonna be in clean
Clean
surface.
Clean
surface.
surface slash, yeah.
So
there's
then I
like
would say
1/16 and then-
The reactive species, the most active species is going to be clean surface, because if I go to the
there is no reacting
Oh,
species.
I see. Okay.
Because that is the active species at that pressure and that temperature.
Yeah,
I
sure.
see.
And it could give you any pressure and temperature and say, where is it?
Yeah.
Because that's like, what else is it going to do? I don't
But that
even
makes
know.
like that's just like reading the graph then. Okay,
Yeah.
okay.
Mhm.
That's easy.
Yeah, I've seen questions where they're like, oh, this graph, what does it mean? And then if ABC, what can you find?
I think this paper came like 2 or 3 years ago, and they were telling us that the questions were mostly related to the graphs.
Cool, that's good. Because I think the graphs are kind of straightforward. Once you get them, they could label them better. Cool. Any questions? That's all I got.
Can we go over the figure 2 one, the one with the lines?
This one?
Yeah.
What about it?
Maybe I'm confused as to how the lines are relevant to these like colored bands, the highlighted bands.
Oh, yeah.
So is it like, I assume clean surface, adsorption, surface oxide or oxide, those are like the oxygen structures, or like, I don't know what we're calling them. I guess oxygen structures that are most relevant.
Yeah.
At these structures, like, okay, now I'm using structure choice, but.
Yeah.
Okay.
So the absorption, adsorption, that's going to be what's in the bulk,
Yeah.
kind of, in that middle gradient layer. And then the surface oxide, that's going to be kind of the bulk surface oxide. Then they have the oxide surface, the literal surface of the oxide. So the thin surface oxide layer is in between the adsorb and the surface oxide.
Wait, repeat that?
Yeah, the 4x4 thin
Yeah.
oxide layer is in between the adsorb and the surface oxide layer.
In terms of stability,
In terms
at that particular environment or something like that? In terms of that environment?
Just in general, like if we're thinking about the layered, if we come back to here, the surface oxide is going to be in between the bulk oxide,
Mm-hmm.
and then all these layers, and all those layers are coming underneath the surface oxide. So
Okay.
if you imagine each one of those layers as one of those lines, that's what it's showing over here.
Yeah.
So the first layer, that's going to be the most favorable species,
Yeah.
as we learned from the first graph. So that's the 0.375. The second layer is that black line. The third layer is the third line. That's going to be the fourth layer. And those are going to be closer. And if you look at where the zero interacts, the dotted line is the zero surface energy. You're going to have the second black line be closer to the adsorb species rather than the surface oxide, and that's going to be less favorable because it's lower. Meaning that
So whatever's lowest, less favorable.
Huh?
Whatever's lowest, less favorable.
Yeah, whatever has the lowest surface energy for a higher chemical potential is going to be more favorable.
But these are for specific, like, temperatures you're
environments.
using. Yeah, that's what I mean by environments, okay.
Yeah.
Lowest
Cool.
surface energy.
But then, there's talking about, and then this is what's gonna be most favorable at these certain, and that's why there's like a limitation, because you can only get like a good surface oxide that's reactive and can help with catalysis at like temperatures like 500 Kelvin or something like that.
Yes.
And that's the main issue that
Yeah.
they found came from this paper is that.
Or the explanation on why these specific reactions, like the epoxide and whatever, work for silver, even though it weakly binds.
Because because the epoxide works at 500, but there's another one that works at 900 or something, right?
Yeah, but
That's
that
what's
uses a
happening.
different mechanism that basically say we don't understand why it works. Sorry.
Oh, yeah,
So-
okay.
Which I think is hilarious.
I think it's
Um,
coming back to
But this
me.
is giving an explanation on, okay, this is why the silver works. It may weakly bind, but there's this surface oxide layer that more strongly binds than every other thing.
Mhm.
So it binds with 3.9 electron volts, which is the highest for the oxygen silver species or system. But in comparison to other good catalysts, that's pretty low.
Mhm.
So that's why this specific surface oxide thing works for silver in these very specific conditions, but why usually silver kind of sucks.
Mhm. Okay.
Because it's the other mechanisms of the oxide or the like absorbed section that does most of the catalytic stuff, which means it's crap.
They don't give like the binding energies for any of the other things that might exist, right?
Not really.
Okay. They're different because they'd be at different temperatures, and they're only focusing on those two.
Yeah.
Things. Okay.
So they, like in the conclusion, I actually really like this conclusion. If you don't read anything, I just read the conclusion. Because it basically just sums up what they showed of like everything else was energetically crap and unfavorable, and then the oxides, you have different layers of oxide, and those oxides will be catalytically active at different pressures and temperatures.
By
Oh,
layers,
that's
you
the
mean-
1/4, 1/9, 1/16
That's
oxides.
Yeah, but those aren't really ever going to be active. Kind of.
By layers, do you mean like physical, literal layers, or just layers related to like this sort of thing? And this?
Related to the phase and temperature diagram.
Okay, cool. All right, nice.
But like, will those exist within layers in the system? Yeah.
Oh.
Like if I think about.
What's more or less favorable? Because like the further, like you said that the surface is like the most. It has to be the most stable one or something.
Yeah, whatever surface species is prevalent. So if you think about this one again, if you're looking at a cross section of a silver interface, you're not going to see this.
Mm-hmm.
You're gonna, at a certain pressure and temperature, you're gonna do a cross section, and you're gonna see a bar of silver, and then you're gonna see one of those things. So if I'm in the surface oxide section, I'm gonna see a block of silver, and then I'm gonna see the surface oxide.
Yeah.
So, and that depends on how much oxygen is either in the system and the pressure and temperature. So with a lot of these reactions, you input oxygen, because you usually just use like bulk silver.
So they're talking about certain like lattice sites and everything, but those were just like unfavorable at the temperatures.
Some of them were unfavorable always.
Okay.
So if we go here, this is
Oh yeah, like
the
all the way
actual-
upper left. Yeah.
Yeah, these are like the actual structures, regardless of temperature. Will these structures exist or not? So this is saying most of them won't. The only ones that like will exist, you know, in the universe at any given pressure and temperature. Why are they most favorable for that pressure and temperature? I don't know, but it's saying these can exist. So it's saying the oxide structures are the most likely to exist. Whereas the bulk substitute, the surface substitute, the bulk oxide, the ozone, those are all unfavorable structures
Okay.
in general, regardless of pressure and temperature, and should not exist.
So back to that line graph,
Yeah.
looking at the 0 line, we're seeing at adsorption, the 4x4 is that red line, the 0.375, and then the like line below it is the what 1/4. Yeah.
Yeah.
So they're saying that the 4x4 is more favorable at that adsorption area or whatever.
Yes.
Okay.
Yep. And then if you look to like the surface oxide stuff, when you have more oxygen, that's going to be more favorable.
Then you get like the other 3 lines become more favorable.
Mhm.
Okay, I see.
And that's going to have a different structure.
Yeah, so the questions there, I don't know about necessarily for like the exam, but I guess for the exam it's like do they want to know like at which, like at the absorption, like which structure is more favorable, or is it like, okay.
Yeah, it could be anything.
Yeah. They might say what is the least amount of surface energy? And it's like, I can't really tell you from that graph. You know, because it's showing a range of surface energies.
Yeah.
So, I think as long as you're like cool with the thin oxide being favorable at that specific pressure and temperature, and that other things will become more favorable at different pressure and temperatures, I think that'll be fine.
I see. So it's like you're looking like mainly it's like what's changing is temperature and pressure, and it's like okay if someone's like different temperature and pressure, like the formaldehyde reaction, you're gonna get a different or oxide structure that's more prevalent because you're just gonna see silver and then like that oxide structure, and then at a different temperature and pressure of some other reaction, you'll see silver and then some other oxide structure.
Exactly.
Okay.
You can think of
That
this
makes more
graph
sense.
instead of chemical potential, you can think of it as temperature.
Yeah.
So you can think at 500 degrees, you're going to be seeing the red line, not the black lines. Cool.
Wait.
Is there anything that would even go up that high though?
Oh, red lines because you're saying the red,
The 4x4.
at the surface. Oh yeah. Yes. Okay.
Cool. Yeah. But they should have colored these different.
Yeah.
Why are they
Because
all
then
red?
at a different temperature and pressure, at the surface oxide, you're gonna see the other 4x4 makeups, the 0.75 and 1.25.
Well, those aren't 4x4. Those are more bulk
the
oxide.
2x2 one that they were talking
Yeah,
about.
there's bulk oxide in parentheses, but you're gonna get different structures of the bulk oxide depending on how much oxygen's in it. So it's
Yeah.
gonna sponge up.
Yeah.
different amounts.
Okay.
There's surface oxide and oxide surface.
Well, there's
Realms.
surface oxide, meaning there's oxide on the surface, and then oxide surface is the surface of the oxide that can react with things.
Ah, okay, I get it.
Whereas the surface oxide is oxide that is on the surface of gold or silver. God damn.
Okay, I understand. Okay, and adsorbed is just what?
Adsorbed is the amount of oxygen that gets incorporated into the bulk silver or a specific layer
Okay,
it's a silver matrix with oxygen absorbed into it
okay.
or incorporated into it.
Nice.
Yeah, then the clean surface adsorption, surface oxide correspond with the other graph where you see clean surface adsorption, surface oxide, and then bulk.
Yes.
Okay.
Okay.
Everyone good?
Yeah, like this question was asked in 2018, but this paper was asked in 2018, but we don't have the PDF of the questions.
Not yet.
I was told it was just the graphs. Probably someone who took it a long time ago.